back to the channel. Today we're going to look at how GeoChemFoam handles heat transfer in microcity style geometries. For this, we'll start from tutorial 5 from the GitHub wiki, Bentheimer heat transfer. But instead of Bentheimer sandstone, we will use a different geometry, a Kelvin-cell. The image we will use in this tutorial was created using the porous microstructure generator, which is developed by Daniel Niblet and the team at the University of Newcastle. So big shout out to them. Go check them out. Link in the description. They're doing amazing work. Now, when you model heat transfer in porous materials, you essentially have two domains, one for the fluid and one for the solid. And the heat equations are slightly different because in the fluid, we have convection and conduction, and in the solid, we only have conduction. These equations are coupled at the fluid-solid interface by a set of boundary conditions, typically continuity of temperature and continuity of heat flux. Now, in a traditional open foam workflow, the standard way to handle this is to create two meshes, one for the fluid and one for the solid, and couple them across the interface. That can work well, but there's a catch. The two interfaces need to match exactly, or at least well enough, for this to work. And in complex geometries, especially when you're working with microcity images and using tools like SnappyXmesh, getting two matching interfaces is honestly really hard. Instead, in GeoChemFoam, we use a volume of solid approach. The idea is simple. We mesh everything, fluid and solid, in one single mesh. And we describe the fluid-solid interface in terms of what we call epsilon, the volume fraction of fluid in each control volume. Once we have epsilon, we can compute the velocity field in the whole domain using, for example, the Darcy-Brickman-Stokes approach, exactly like in the previous video on this channel. And of course, we should get 0 in the solid. Now, for temperature, we want to do something similar. One mesh, one equation, one field. And for this, we start from the fluid and solid heat equations, and we apply volume averaging. When we sum the two equations and we apply the immerse boundary condition, we get one single field equation that can be solved everywhere in both phases on one single mesh. And the only thing we're missing is a model for the heat conduction inside interface cells, which will be some sort of average between the heat conduction of the fluid and the heat conduction of the solid. So now let's jump into GeoChemFoam and see how this works in practice. All right, here we are in the GeoChemFoam runs folder. I'm going to start by copying the tutorial, which is in tutorial, heat transfer, heat transport foam, Bentheimer, and I'm going to call it Kelvin-heat. Now in Kelvin-heat, we have the usual open foam case structure, so constant and system, plus a set of GeoChemFoam scripts that automate the workflow. So let's start by opening the create mesh script. This is where we define the image properties and the meshing strategy. I covered this process in detail in the previous video on the channel, so if you haven't watched that one yet, go check it out. Here, I'll move a bit faster. The image we want to use is in the GeoChemFoam image folder. So here, in row, and it's called Kelvin 200. what we can do is open the text file to see its metadata. So it's a 200 cube image. The resolution is 10 micron. It's not a grayscale image. It's a phase labeled segmentation with two phases. Pores are labeled as 1 and solid are labeled as 2. So we want to put this information inside the createMesh file. So the image name is Kelvin-1 200 by 200 by 200. It is in this directory, it's in raw format, it is compressed, and its dimensions are 200 by 200 by 200. Next, the segmentation. It is not a grayscale image, so we can comment this. The properties of a grayscale image, and uncomment the one for the phase segmentation. So for this image, pore is 1, solid is 2. There is 2 phases only, so we can remove these third phases. And here, this is the porosity of each phases. And for the pores, it's 1. And for the solid, it should be 0. But of course, we can't put 0 here because it will trigger a division by 0. So instead, we put a small number, 1 in minus 4. We are going to simulate the full image, so we could keep the cropping parameter to 0, 200 in each direction. We are going to remove the pad. We won't use a pad here, which means that we have to select a pressure boundary condition later in case flow. The resolution is 10 micron. And next, we define the mesh properties. And we could go straight to 200 by 200 by 200, matching the voxel size. But here, I'm going to be a bit smarter and use local mesh refinement. So I will start with a coarser mesh, 100 by 100 by 100. This has to be a clean factor of 200 for the refinement strategy to work, so 100 will work. This means the base mesh resolution is 20 micron. So next, we enable local refinement. So this is going to refine cells that are around the interface. If we put n level equal 1 here, this means each cell at the interface is going to be refined once, and we will recover the 10 micron resolution where it matters the most. We set n level equal 1. And for the layer, I will put 2. This controls how many layers of cells around the interface are refined. 1 means only interface cells, and 2 means 1 extra layer on each side, which improves accuracy. Then you have those 2 parameters, refine Stokes and refine solid. If you put 1 here, you will fully refine the Stokes phase, so the pores, or fully refine the solid phase. Here, we won't do this, so we keep it at 0. And the last parameter to change are the number of processors in each direction. I have 64 cores in this machine, so I will use 4 processors in each direction, giving me a full 64. And now we can come out of there and run our createMesh file. This should only take a few seconds. And when it's done, we can open ParaView, and we will open our test case. So we get the typical output message here. This is because we need to select a decomposed case. We've decomposed our case. I'm going to unclick skip 0 time because I want 0, and I'm also going to unclick this, the create cell to point filter data. This will make things slower, and I don't need this. We'll click on apply, or domain will appear, which is a box, of course, and we can look at the parameter epsilon, and we can see the pores or flow channel in red and the solid in blue. we can look at surface with edges to look in detail into our mesh, and we can see that we have refinement around the interface. Now, just for fun, let's separate the two regions. We will use a threshold filter, so this button here. We're going to select every cell below epsilon equal 0.5, so every cell in the solid. Okay, so we can see our solid phase, and I'll split the screen and do it again, but instead of below epsilon, I will choose below 0.5, I will choose above 0.5, and we will obtain only the pores or flow channels. So on the left, the solid, and on the right, the flow channels. Then we go back to our terminal, and I'm going to clear it to make some space, and now open the init case flow file. And here we decide the flow properties. And first, the boundary type. Since we didn't put a padding, we don't have a choice. We need to use a pressure drop boundary condition. Otherwise, we will be flowing inside the solid. Obviously, this will not work. So we decide pressure drop. We can put the flow rate to 0. This will not be used. And for the pressure drop, I will use something small, E-4 for example, because I want a low Reynolds number, ideally below 1. For the kinematic viscosity, I will use 1 E-6, which corresponds to water. And next, we define how permeability is computed from the image for each voxel. And here we're using a phase model, so we will comment the grayscale and put again the property of our phase, so it's just two phases, and the porosity is 1 and 1 E-4. And for the permeability, we will put a large value in the pore, so 1/12 is good enough, and a low value in the solid, 1 E-26, is low enough, so we can keep this property like that. And then I'm going to comment the Cosmic-Kalman constant because I don't need it here. I will then run init case flow, and then we're ready to run case flow. And this will take about a minute to run on 64 processors. When it's done, we run process flow, and this will give us poroperm.csv with the porosity, the permeability, the Reynolds number, which here is about 0.3. And now we can move on to heat transfer. I'm going to clear my terminal again and open init case heat. And we need to start by defining the initial and boundary condition. Here T0 is the initial temperature, and Tin is the injecting temperature. They are dimensionless, so you can rescale later. This doesn't change the physics. By default, it starts with 1 and we inject 0. I'm going to flip that because I want to inject hot into cold. So start at 0 and inject 1. Next, the boundary condition on the external walls. By default, it's a fixed value equal to the initial temperature, and I'm going to change this to a 0 gradient. So there is no transfer through the outer boundaries. Now we choose the diffusion model for the interface cells. This controls the effective conductivity, and harmonic average will be a more accurate. Sometimes there's robust model, and arithmetic is more robust and less accurate. So here we'll keep harmonic. And next, we need to define the material properties. Now the default values here correspond to something like supercritical CO2 and quartz, which is fine, but for this tutorial, I want something more dramatic. So I'm going to use water as the fluid and a very conductive metal like silver for the solid. So for water, kappa F is 0.6 watt per meter per Kelvin, density 1000, and heat capacity 4180. So this corresponds to the water properties. For the solid, we put a very high heat conductivity of 400 watt per meter per Kelvin, large density of 10,000, and a heat capacity of 200. This corresponds to a silver-like material, give a very strong contrast with water. All right, we save and we close, and we can run init case heat. And now we open run case heat. And we need to choose how long to run the simulation, when to stop for a report, and what time step to use. And because the solid conductivity is so high, the thermal response will be fast, so I will just run this for 0.1 second. We will write every 0.02 seconds, so we get 5 steps. And we will use a time step of 2 minus 4 seconds here, which means 100 steps for each report, which is good enough. So save again, and we run case heat. And again, this should take about a minute to run on 64 processors. And when it's finished, we can go back to ParaView, hit refresh, and look at the temperature at the last time in each domain. So for the solid and for the pores. You can see on the left the temperature in the solid part, and on the right the temperature in the flow channel. And we see exactly what we expected, a fast diffusive wave through the solid lattice and a slower, less advanced temperature field feed. We can also see the fluid is heating up around the solid struts, while the core of the channels stays colder for longer. There we go. That's the end of the tutorial, guys. Thanks for watching. And if you found it useful, go on and push that like button for me. And I would also like to know, what are you guys using for heat transfer? If you have a strategy that works, put it in the comments. Subscribe if you want more GeoChemFoam content, and I'll catch you in the next video. But until then, keep it open, keep it reproducible, and happy modeling with GeoChemFoam.